Okay, this is strain example number 13. This one is another indeterminate problem, but that adds a twist to it, in that we have an indeterminate problem that also includes thermal strains or thermal expansion. Problem reads, two elements are stress-free when they are welded together at B and welded to rigid walls at A and C. Subsequently, element 1 is heated by an amount delta T, while element 2 is held at the reference temperature. Write an expression for axial force in the bars as a function of the temperature change delta T and material geometric properties of the elements. All right, so let me switch over to OneNote where I can do some sketching. And I'll zoom in here just a little bit. Okay, so we have the problem statement. We have the sketch of the problem. So E is constant, same material for both element 1 and element 2. We have two cross-sectional areas, A1 and A2. The diameters aren't given, the lengths aren't given, etc. So, like the other problems that we've dealt with, the first thing I'm going to do is start with statics. But in this case, we don't have an interface plate like we did in the previous example. So what I'm going to do is I'm going to sketch one in here. Even though it's not there, and it doesn't have to be there, I find it a lot easier to work with if there is a plate that I can envision. So I'm going to sketch that plate there. And then what I'm going to do is bring that plate out, and I'm going to draw a free body diagram of it. So here is that plate that I just sketched in. It's between element 1 and element 2. And if we look at the forces that are on there, again, assume that each of the elements is pulling in tension. Then we're going to have an internal force F1, or I'll call it, F2 or P2 pulling to the right like that, and an internal force F1 or P1 pulling to the left like that. So if we write the sum of the forces in the x direction is equal to 0, then what we could find is that P1 is equal to P2. So that is the contribution that we get to this problem from our statics equations. So we have one equation, two unknowns, so therefore the problem is statically indeterminate. Now, if we look at this and we think about a temperature change that's positive, in other words, it gets hotter for element number 1, then element number 1 is going to grow, and it's going to go into compression. So these member forces that I've drawn in here are backwards from what I would expect, but they're drawn correctly from the sign convention point of view that tension is positive. So that's why I've done that. All right, so the next step here would be to look at geometric compatibility. And let me go ahead and zoom in on this sketch some more. As this thing gets hotter, element number 1 is going to grow in length. And what's going to happen is it's going to, let me erase that. It's going to tend to cause that interface plate to shift to the right. And so the black represents the initial position and the blue represents the final position. So this displacement is already drawn in there, I guess, is going to be delta B, just like that. So let me zoom back out a little bit. I'll shift back to black. And what we could do is we can write our geometric compatibility equations. Didn't spell it right, but that's okay. Like that. And what we have is our displacement delta B. And if that plate B moves to the right, that means that element number 1 has to get longer. So we say that that's equal to little delta sub 1. Since it's getting longer, that's positive. And if it moves to the right, then element number 2 has to get shorter. And if it gets shorter, that's negative. Tension is positive, so an elongation is positive. Compression is negative, so a contraction is negative. So this represents our geometric compatibility relationship. Delta 1 is equal to the opposite of delta 2. As AB gets longer, BC must get shorter by the same amount. All right, then let's look at our constitutive relationship, our force deformation relationship. I'll use the more formal term this time, constitutive. There we go. Like that. All right, now we know that delta is equal to P times L divided by A times E. If we go to our equation sheet, you can see that, let's see, right, there's our equation for delta. It's equal to PL over AE. But we also have a expansion or contraction due to temperature change as well. So we can expand on this, and we can say that that's equal to the thermal coefficient alpha plus the change in temperature delta T times the initial length, L naught, or L. So when we have that constitutive relationship, we have a force deformation relationship as a function of the load that's on the member, but also as a function of the temperature changes on the member. So then what we can do is we can do substitution now. I'll write that in blue, back substitution, or just substitution. And what we're going to get is this. So we get delta 1 is equal to the opposite of delta 2. So we get P1 L1 divided by A1 E1 plus alpha 1 delta T1 times L1. And that's equal to minus P2 L2 over A2 E2 minus alpha 2 times delta T2 times L2. Okay, now a couple of things that we can do here. Okay, so the first thing is that there is no temperature change in bar number 2, so that goes to 0. So that simplifies things greatly. And then next what we can do is we can solve for the internal member force. And since we know that P1 is equal to P2, then we can just say that that's equal to P and that's equal to P as well. All right, so I just substituted in from our statics equations. So now what we can do is solve for P. So what we can do is I'm going to start with the part on the left here, and I'm going to say that P is, let's see, how do I do this? All right, so P times L1 over A1 E1 plus P times L2 A2, whoops, divided by E2 plus alpha 1 delta T subscript 1 L1 is equal to 0. Okay, then I can pull that out. So I end up with P times L1. I can actually do this, P over E, because E is the same for both pieces. So L1 over A1 plus L2 over A2, like that. And then plus alpha 1 delta T1 L1 equals 0. All right, and if we solve for P in this case, let's see, we can bring that over. So let's see, we can take, okay, so now what I'll do is I'll solve for P. So we could say that P is equal to, let's see, it's going to be minus E times alpha 1 delta T1 times L1, all divided by the ratio L1 to A1 plus L2 to A2, like that. So this force gives us a negative answer for a positive change in temperature. So that means that we end up with a compression when we have an increase in temperature, or when we have a decrease in temperature, a negative value of delta T, and then we end up with tension in there. All righty. Thank you.